So just to catch everybody up here, we have been looking at uniform circular motion so far. And so this should be a familiar story to everybody. When we have uniform circular motion, the acceleration is pointed towards the center, Latin word centripetal, or center seeking. And the magnitude of the acceleration is v squared over r. So we could draw a picture that looks just like this. The velocity is tangent, and the acceleration is perpendicular to that tangent. What we're going to consider today is what happens if you are moving in a circle, but your speed is not uniform. If you're driving around a racetrack and you're speeding up or slowing down, how does that change things? So here we go. Let's get ourselves a circular racetrack like so. And we're going to put a car on it. And let's have that car go from 0 miles per hour to 60 miles per hour. Or let's put it in metric, 30 meters per second. Probably a better way to do this. Should be 66 miles per hour-ish. In a time of, how fast should we go from 0 to 60? Maybe in 10 seconds? So what you can see is that if our car is going this way, then what we have is an instance of non-uniform circular motion. The car is moving in a circle, but also it is increasing in its speed. Okay, so how do we deal with that? The way that we're going to deal with it is to think of it like this. We are going to break the motion into two independent components. We're going to consider acceleration that is parallel to the direction of motion, or in other words, in the direction of the motion. And we're going to consider acceleration that is perpendicular to the direction of motion. In other words, we're going to have a reference frame in which we are moving with the car. And we're going to think of this whole track around as being kind of like a straight line. It's not a straight line, obviously, it's curved, right? But as the car goes, we're going to be going with the car. Can you sort of visualize that in your mind? You can sort of picture yourself in the driver's seat looking out through the windshield, and here you go. And so at any moment, you're moving forward, right? That is the direction of motion. That's the parallel to the direction of motion. And here's what I claim. I claim that the acceleration in the parallel direction, A parallel, has the effect of changing the car's speed. Whereas the component of acceleration that is perpendicular to the car's motion has the effect of changing the car's direction. Changing the car's direction. Now, just to illustrate this, I can't really put a demo on video, so I'm going to ask you to sort of imagine. If I have a car that is going in this direction, and I come along and I give it a mighty push here, then I think it's pretty clear that that mighty push is going to speed the car up, right? So this is acceleration that is parallel to the car's motion, changes the speed. But now I want to consider a separate situation in which we have the car going forward like so. And now another car comes along and hits it from the side. And when it hits it from the side, what it's going to do is not change the car's speed, it's going to change the direction in which it's moving. It's going to bend it down, bend the motion down. So perpendicular to the motion, acceleration perpendicular to the motion changes the direction. And the cool part about this is that we can evaluate these components independently of one another and then put them together into one vector at the very end. And it's not too hard to do. Does everybody understand the parallel perpendicular distinction? Does it make sense, physical sense? Okay. Now, how do we deal with this? Well, actually, it's fairly easy. Because the perpendicular component of the car's motion is nothing more, if you take a look, here's my circle, right? Here's the velocity. The perpendicular component of the acceleration is pointing in which direction? Towards the center of the circle. And we already know what the value of the centripetal acceleration has to be, and that is v squared over r. So, A perpendicular is what it has always been. It's going to be v squared over r. But actually, A parallel is not too difficult either, because that's going to be the rate of change of speed. So here's my A parallel. And that's simply going to be the change in speed over the change in time. So we actually have an easy way to compute both components of this. And now if you take a look over here at what we have a vector with two perpendicular components. And we can add those two perpendicular components together over by this much and up by that much to give us a vector that points like so. This is the total acceleration of the car. And it has a centripetal component like so and a parallel component like so. The centripetal component makes it go in a circle. The parallel component makes it speed up. Or, if it's pointing that way, it would make it slow down. Does that concept make sense? So let's come back now to our car that's going around the racetrack and put some numbers to it. Here we go. We already have some numbers. We know that it goes from 0 to 30 meters per second in 10 seconds. Let's give a radius for our racetrack. And I think a reasonable radius might be something like, I don't know, 200 meters? That ought to do. It's a pretty large racetrack. Twice the size of your soccer. 4 times the size of your soccer field. Pretty large racetrack. Okay. And so now we wonder, what is the total acceleration of this car? And let's evaluate that total acceleration at 3 different points. At point A, at point B, which is halfway, 1/4 of the way around, and at point C, which is halfway around. I need some space. So I'm going to copy this whole diagram here. Group it. And copy it. And paste it. There we go. So here's our setup. We have the car going around the circular track. It goes from 0 to 30 meters per second in 10 seconds. And we want the total acceleration, A, at point A, point B, and point C. Okay. Now, first of all, let's use a little bit of common sense. If we assume a constant change in speed, then what will the speed be at point B? 15 meters per second, yeah. Good. And we're going to need that speed because that speed is going to be necessary in order to compute the centripetal acceleration. So let's compute our acceleration components separately. First of all, let's talk about A parallel. A parallel is going to be the change in speed over the change in time. And that's easy enough. It's going to be 30 meters per second over 10 seconds, or 3 meters per second squared. We're going to assume that's constant for the car, so it's going to continually gain speed at that rate. So in other words, this applies for all 3 points. A parallel is 3, A parallel is 3, A parallel is 3. Is everybody comfortable with that part so far? And this is the part that we would actually sort of experience if we're in the driver's seat, we're driving down the road, and we watch our speed increase from 0 to 15 to 30, and we compute a rate of change of speed of 3 meters per second squared. Now, what about the A centripetal? That's going to change as the car goes around, because the A perpendicular, or A centripetal, has a magnitude of v squared over the radius. And at point A, then the v is 0 miles per hour. So we have 0 squared over 200 meters, and A perpendicular is therefore equal to 0. But at point B, we have a speed of 15, and therefore my v squared over r is going to be 15 squared over 200. Somebody give me that number. Yeah. 125. Yeah. So I get 1.12 meters per second squared as the centripetal acceleration. And then in C, our speed has gone all the way up to 30, so that I get 4.5. I believe I get 4.5, right? Yeah, meters per second squared. And so we ask, why is the centripetal acceleration increasing? It's because the speed is increasing. And so it takes more acceleration to keep the car going in a circle as opposed to just skidding off the track. Does that make sense? So at some point we expect probably that the car will go so fast that its tires can't provide that acceleration, and what happens at that point? Straight off the raceway.
Hopefully it'll slow down for that and keep his top speed.
Something like that. Yeah, I'll hit the wall, something like that.
So is this part of it how those like motorcycle guys can go around the circle on the inside of the circle?
Bingo. That's exactly it. Yep.
So you were saying if the tires can't support acceleration, what does that mean? Like,
Well, the tires have a certain coefficient of friction, right?
yes.
So actually, once we're done with this, let's address that question directly, because we'll have just enough time for that. That's a great question. I want to draw the various accelerations that we have. Take a look at point A. The parallel is 3, the perpendicular is 0. So the way in which we draw it is we're going to treat this way as the parallel and that as the perpendicular. So we're talking about 3 over and 0 in the perpendicular direction. So this is what the A looks like at this point in time. But when we get to a speed of 15, now we have 3 in the parallel direction and 1 in the perpendicular direction, so that my acceleration now looks like this. It's starting to bend inwards because we're getting more of a centripetal component. And then finally, when we get to point C, we have 3 over and now 4.5 in, so that my acceleration is much more like that. And you can see that as I get faster and faster, my acceleration is going to become closer and closer to straight inwards towards the circle. Yes?
So for when we use this acceleration in our equation, would you calculate the magnitude of it, or how would you?
Yeah, you could calculate the magnitude, and that would be a simple matter of doing the usual Pythagorean theorem. So if I wanted the magnitude of the acceleration at b, that would be the square root of 3 squared plus 1.12 squared.
Is that what you would plug into your equation? F equals mn.
Oh, to get the magnitude of the force, yeah. Yep. Or you could do separate components of force, either way.
So you could just leave it in there.
Yep. Exactly so. Now, as I said, this is the tip of the iceberg. When we do this in physics, we have a kind of convenient way to break it all down and componentize it. But I think it's too much math. So we'll leave it like this. Okay? Now let's address Peter's question, because it was an excellent question. And that is, how do the tires relate to this? So what I'd like to do is I'd like to take our racetrack, and I'd like to look at it now from a side view. So here is the racetrack, and here is the car on the racetrack with its tires.
Are we talking about bank corners or regular?
Regular, unbanked. That's a great question. Banking, what banking does for us conceptually is it allows the normal force to provide some of that centripetal force, takes away the friction requirement.
Probably a slight uphill.
Yeah, that's exactly it. So we're going to pretend that this is flat. And so now we wonder if the radius is 200 meters, as it was, and the speed is 15 meters per second, as it was, then what is the minimum value of mu so that the car does not skid? Now, civil engineers will ask this question in reverse. They're going to start with typical values of mu for tires, and they'll ask, what is the maximum speed that you can go around the corner and still be safe? And then they'll chop a few miles an hour off of that and put it on a yellow sign and post it right on that curve. And they'll do that for tires on wet pavement because they want to have the worst case scenario, right? So how would we do this? How would we go about solving this? Before that, we need free body diagram. There we go. I was hoping somebody would say this. So we have M and mg and normal force. Now, this is the side view. Which way is the frictional force going to be pointing? The car, it's going to be pointing really this way, isn't it? In towards the center of the circle. So we actually need a top view. What's that?
Unless you can draw 3D.
I can't. Yeah, totally incapable of that. And actually our top view is, let's make it consistent with what we had. This was at point B. So let's have our car like this. Top view, and we said that the acceleration was pointed kind of like this, wasn't it? Right? And so that acceleration is going to have to be provided by the only possible force that is operating in that direction, which is friction. So we're going to have a force of friction right here. And that force of friction is going to have to partly keep the car on the road, and that's the centripetal component, and partly help the car as it speeds up. And that is the parallel component. So there's my frictional force. Okay. Now what can I say? Well, from the top view, from this one, the sum of forces is equal to 0, clearly, because my car is not floating. And so therefore I conclude that the normal force is equal to mg. Kind of a familiar result, right? Over here, the sum of forces is equal to mass times acceleration, and I can pull the acceleration from the result that we had in the previous part. 3 in the parallel and 1.12 in the perpendicular. And I'm just going to write that as 3 comma 1.12. And here, my axes are rotating with the car. So I'm using a car reference frame for that. 3 in the parallel and 1.12. Well, now I also know that this is the one single force of friction, and I know that the force of friction is less than or equal to mu times the normal. And that's going to happen, that inequality is going to happen for each component. And so therefore, the normal force is mg, right? And now something happens that we have seen a lot, and that is that my masses cancel out, so that the mass of the car doesn't really matter. Well, how do I interpret this? I'm going to interpret it like this. Let's do it in terms of magnitudes. I think you were right, James, that we would have magnitudes here. And that's going to be mu times g has to be less than or equal to the square root of 3 squared plus 1.12 squared. And let's get a number for that, if you wouldn't mind. Oh, my inequality is wrong. It needs to go
Shouldn't it be about 3.25?
like that. There we go. Much better. What you got? 3.2. 3.2. So that my mu has to be greater than or equal to 0.32 in order for the car to stay on the road and continue to have the acceleration that it has. Now, how did I get the sense of the inequality wrong? I forgot that force of friction is less than or equal to mu times the normal. I wrote it as greater than or equal to, which was silly. Okay? Does that answer your question?
Kind of. So, can you relate that to like number 9, which is the
So number 9 is going to be similar, except that you're going to be in luck. You're not going to have any parallel component of acceleration in number 9. In number 9, you're looking at uniform circular motion because the car is going with a constant speed.
Okay, so which was the friction pointing though?
It should be pointing straight in towards the center of the circle.
That's the friction.
Exactly so. And so here's, have you ever driven anything sort of fast where it has to hug the road?
No.
Okay. Has anybody ever driven a car a little too fast? Feel it kind of hugging the road? You can basically feel the tires pushing the car in as you go around curves. You know what I'm talking about? And the tires are pushing that car to keep it on the roadway, and they're pushing straight in towards the center of the circle.
Oh, so it's the way. So this the friction is the force of friction. The direction of the force is the same as the acceleration, like the direction.
Yes, because F equals. Yeah, this is a really good point. This is a vector equation. So when I look at the net force, that net force is a scalar multiple of the acceleration. So it's going to point in the same direction as the acceleration. So if my acceleration is like so, my force has to be parallel to it because it is a scalar multiple of. Does that help?
Yeah.
Yep, good question. Now, the bell should have rung, and it hasn't rung, so I don't know what the deal is. But I think we're done for the day. See you.